Okay, so we're going to be talking about acid and bases. And it's mainly acid and base equilibrium primarily. But we will be talking about generally acids and bases. You guys are familiar with pH, POH, sorta. POH, yes. It's what? Basic, yeah, that's right. Hydroxide, yes, that is correct. Yes, and we'll be going over it. I'll give you guys the update. We're going to be talking about the relative strengths of acids and bases. Do you think you would ever get rid of it? That's what they were dealing with this last exam. Relative strengths of acids and bases. Yes, yes, they look like they're going to cry because of it. Hydrolysis of salts, which again is just basically the separation of ionic compounds. And if we think about acid and bases are just ionic compound where you have hydrogen as your major ion, the hydrogen ion, or the hydronium ion. And then polyprotic acids, which polyprotic acid basically means poly means many, protic means protons, so many protons. We'll talk about buffers, and we'll also talk about acid-base titrations. There are many protons running around, yes, many protons. All right, because if you think about the hydrogen ion, right, H plus, what is it? It has a proton. It doesn't have an electron. It doesn't have a neutron. So that's what they mean by many protons. Okay. So here, this is basically a sinkhole. Now, if you look at the sinkhole, it actually has both acidic properties because it has acidic groundwater. So if you actually test the pH of that water, it'll probably be like a pH of like 4-ish, 3, 4 or 5-ish. And then you also have basic rock formation. So that's going to actually act as our basis. So I guess let me get a. Holy crap, it didn't crash. We're doing good. Okay, we just fought with the, it's like if it's in one thing, it's going to be another, right? Yeah, so basically the rock formations are going to be your base because they're going to be basically sit there and test those are going to have pHs that are going to be greater than 7. Right? So for instance, limestone. Okay, so first thing that we're going to be talking about is the Bronsted-Lowry acid to base. So when we first were introduced to bases, we were talking about just that. First introduced to acids, we were talking about just that H plus, right? So the donation of H plus. So we're going to kind of change our definition so it'll encompass more stuff, and that'll help you today, and it'll also help you in OChem if you start paying attention to this part here, right? And then we're going to write equations for acids and bases based upon the ionization reactions. We're also going to use ion product constants for water to calculate the hydronium and the hydroxides concentrations. So that's your pKa, your pH and your pOH primarily. And then the last part is that we're going to describe acid-base behavior of amphiprotic substances. You guys know what amphiprotic means? Like amphibian. Amphiprotic. Well, it's not that they think they're water. It's just the fact that you can use water as both an acid or a base. Amphiprotic, basically, amphi means like, interchangeable, kind of. And then protic means like proton, essentially, right? So, in other words, that water can act as an acid, water can act as a base. So that's what essentially means, the definition. So Jans Bronsted and Thomas Lowry, they basically did a definition where they said a Bronsted-Lowry acid is a compound that donates a proton to another compound. And they did this a little bit different because at first we were just looking at it as H+, right? So when we first started looking at it, we looked at it as H+ or the hydronium ion, and that's it. So this kind of broadens it. And so they're saying just a proton. Well, a proton could be H+, but it could just be a proton that's being donated from one element to another. Okay. And then a compound that is an acceptor of a proton from another compound is considered to be the base. Okay, so an acid is going to be a proton donor. And then the base is going to be a proton acceptor. So, as you guys may already know, acids can be both organic and inorganic. Sometimes they're going to be cations that have H. Sometimes they're going to be anions that have H. Right? Just the fact that they're able to get rid of that H, right? And I'll give you an example of that here in a second. And they contain H+. Where bases, they're going to be ionic compounds that contains OH-. They're going to be molecules like primarily amines. They're going to be with or without H. And there's only going to be a few of them that are going to be cations. Okay, so let me give you an example of an anion that contains H. Let's see. So hydrogen sulfate is an example, right? It's an anion, right? Because it's a polyatomic ion. And this H here is able to sit there and be donated, right? So then it'll donate that proton or that H+, right? So acids have been around forever, right? And we've basically known about them in ways, but we often think of them as, things that either taste bitter or sour, right? Like a lemon, or things that cause color changes, dyes. And so that kind of gives us our litmus paper and our pH paper. And then we can also use potential metric measurements to basically measure the difference. And so that's how we get that pH, right? So in that case, we're looking at the charges. Yes, sir. Yeah, you remember. Yes, you guys had such a great time with it. I thought we'd do, another 3 more labs that would deal with titration. And you guys, you would get so the excitement on your faces. We're there. Oh my God, I just overshot it. I don't think I forget. I see it all. So the early form of acid and base theory was basically described by Arrhenius. Arrhenius basically said that it had the H+, ion, or the hydrogen ion, or the hydroxide ion. So Arrhenius acids system basically involved only the hydrogen ions or the hydroxide ions. And so this is basically a very limited view. We needed to expand it beyond that. Okay. So in general, this is the form of the Arrhenius acid dissociation. So HA yields H+ and A-. Right? And that's how we get like hydrochloric acid, right? So HCl. And then the Arrhenius base was described as the dissociation of the OH yields B plus and BO minus. I mean, OH minus, not BO. Okay. So Bronsted-Lowry basically has kind of changed this a little bit, not too much, right? So now we're just looking at the proton rather than H plus only. So in this case, we're basically saying that protons are going to be added. So if we have, in this case, we have water acting as an acid, right? So then its conjugate base is going to be OH, right? Because we're removing an H plus, right? So the acid is a proton donor. Okay. And so here we have ammonia acting as our base. So as it accepts an H plus, it becomes the hydronium ion, right? And so that's its conjugate acid. So together, we always have a pairing. We have an acid, and then on the other side of the equation, that's going to give us our conjugate base. And then here we have the base, and on the other side, we're going to get a conjugate acid. That's right, because you're just, one is going to be receiving, one is going to be, donate. So one is going to donate, one is going to be receiving. Okay, so Amphiprotic species. So basically, when you have species that could either be an acid or a base, or it could either accept or donate a proton. So water is the perfect example. So in the presence of an acid, water acts like a base. In the presence of a base, water acts like an acid. Let me give you an example. Okay, so here we have hydrofluoric acid and water. So in this case, this is my acid, and water is going to be my base. So in this case, we're going to end up getting the hydronium ion, and then we're going to get the fluoride ion as our base. So the hydronium ion is now acting as our conjugate acid, and this is our conjugate base. Simple. So when we have a reaction between a Bronsted-Lowry acid and water, it's called acid ionization, because all you're doing is basically you're forming the ions, right? Okay. Does that make sense? Ionization, formation of the ions. Yes, or autoionization, that basically deals with water, right? Just water alone. We'll talk about that. Yes. Oh, really? Some of the questions on here, yeah. Yeah. Okay. I apologize. But it works the same if you think about equilibrium. It's pretty much the same concept, right? And we'll talk about that here in a second. Okay, so here, water is going to be acting as an acid. So we have, this would be ammonia, 5 carbon, so it's 5 carbon chain, pentaamide. Pentalamide. In the case of, pentyl double, so it'd be pentalamide. So in the case of this 5 carbon chain, this is an amide. So this is pentalamide. And or actually no, this is benzylamide. Clear this. So in this case, this is acting as our base. And so it's going to be, water's going to be donating its proton to this base. And so then we get this guy's the conjugate acid. So if we think about the pairs, the pairing, we have, this is going to be my pair. So that's going to be the base. This is going to be the acid. This is going to be the acid. This is going to be the base. Okay. Questions? Pretty straightforward so far? Okay, good. Now we get to see how well you guys understand that. Okay, so identify the acid, the base, the conjugate acid, and the conjugate base. Okay, do we have some answers? Okay. It's okay. Ugh. Yeah. Okay. Okay, so let's see. That's my acid. This is my base. Yes. Okay, so this is my conjugate acid. Okay. And this is my conjugate base. Who's donating? Who's uh-huh. That's right. It's donating it to this guy. Yeah. Yeah. Conjugate is opposites. Yeah. Yep. Okay. Okay. Does that make sense? Okay, what about this one here? Which one is the conjugate acid? Which one is the base? Or which one is the acid? Which one is the base? Which is the conjugate acid? Which is the conjugate base? Okay. Okay. So then who's the conjugate? Acid. Are you sure? Conjugate acid. It means that the equation is going both directions. It's an equilibrium. Yeah. Yeah, it's before they actually had the both errors on the thing. So yeah, it makes it a lot easier to understand, doesn't it? And then here. Okay, what about here? Acid, base. Conjugate acid, that's right. Okay. 10 and 11. Is there 8 of each? Okay, the next one. You said this is acid. This is the base. Okay. Okay. What about this next one? that water's acting as both? Yeah, I mean, in a sense, well, in the sense water's able to act as both, but here, water's acting as one. What is it acting as? It's an acid, that's right. The product is you're going to have both. You're going to have, this is going to act as your conjugate acid and your conjugate base, right? So that's Ca/Cv, right? Make sense? Right, because literally you're getting two products. If we put the H over here, you're getting the OH minus, and then from this product, you're also getting the OH minus. So it's acting as both, since there's two of them. Right? You see that? Okay, F. You said this is a good one? Acid for this one. And you said base for this one?
So is the whole thing an acid, for example, for the first step, or is it just that H2O that you're putting that H for?
No, the whole entire thing would be considered an acid if you consider it an acid. Do you guys really consider it an acid? Look what's happening. So how many of these do we have? We have 3, and then there's an OH, and then we're going from literally from a +1 to a +2. What's happening in this case? It's accepting a proton. So is this really an acid? It's a base. This one is tricky. So that means that this guy is the acid, right? And we can also, like, if we pay attention to the charges, that also helps us out, right? Okay. So this would be my conjugate acid. This is my conjugate base. Okay. Last one for the goal. Acid, base. Agree? Are you ready? We're ready to move on. Everybody got it down? Okay. Okay, so autoionization. So this is what you were talking about earlier, right? So if we think about water, in this case, we have water that's acting both as your acid and your base. So in one case, if the acid is donating a proton, then we end up with the hydronium ion, and we end up with the hydroxide ion. Now, the products for this are always going to be constant. So they're going to always have a constant value of 1.0 times 10 to the minus 14. So if we have Kw is equal to the concentration of the acid, the conjugate acid, and that's equal to the conjugation, the concentration of the base, right? So then what is going to be the value of each of the individual components? So what is going to be the concentration of this guy and this guy at equilibrium? Well, this value is constant, yes. So that's the constant, that's the equilibrium constant, which is going to be 1 times 10 to the minus 14. So then what is going to be the value of this at equilibrium? How would I figure it out? You guys have that look. We've been doing equilibrium. You should know this now. Like the back of your hands, right? What's that? Ice table. Well, in this case, you're starting off with just water. This is just H2O, right? So what is the rule about something that's pure water? Pure. What would be the symbol for water? It would be a liquid, right? Okay, do we use that in terms of equilibrium? Okay, so, and then at equilibrium, we have this made and this made, right? So how would I calculate the concentration of each of those? So we know that if we did the ice table, so we don't take this in consideration. Initially, there's 0 of this, and there's 0 of this. C would be what? Okay. So then this would be X, right? And then this would be X, right? So then E is just going to be X, right? Okay, so then I get Kw equals X squared. So then X is equal to what? Which is equal to 1.0 times 10 to the negative 14. So then X is equal to, what was that? Okay. So if we take the square root of both sides, square root basically means we divide this by 2, right? So that's going to be 1 times 10 to the minus 7. Okay, so if we think about that, right? So if the concentration of water being ionized is -7, then if we calculate our pH is going to equal the concentration minus the log, the concentration of H3O plus. Okay. So what would be, plug this in, minus log times 10 to the minus 7. What is that going to equal? It's going to be 7, right? So we know what is the pH of water? 7, right? And this is the reason why. It's because it auto-ionizes. So its pH is equal to 7. Okay. Okay, so that basically means that when it autoionizes, you have equal concentrations of the hydroxide ion, and you have equal concentrations of the hydronium ion, right? So they're exactly the same. This is kind of cool, right? So this allows us to sit there and set our table, right? Because we have our table for pH from 0 to 14 because that autoionization. So that's the reason why our scale only goes up to 14, and that's why it starts out at 0. Okay, so does that make sense? Okay, cool. Mhm. In theory, yes, long as you have an H plus that's being donated, right? Julie, yeah, that look. Okay. I don't know what to tell you because I don't know what you have. So, yeah. Okay, so let's keep going. Okay, so clear. Let's clear this. So that kind of explains the that whole concept of acid, base, neutral. We know that pH 7 is neutral, right? So anything that's below pH 7 is going to be an acid. Anything that's going to be above pH 7 is going to be a base, right? And it's because of that scale. So if you think about it, if the concentration of H plus is greater, right? Greater than 7, then we know that that is going to be acid, right? Because that's how we get closer and closer to 0. Right? And then if the concentration is less than 7, we know that we're favoring the OH. And then the POH is going to be greater than 7. Does that make sense? Okay. So let's show you. Let me see if I can show you how that works. So we already talked about the autoionization and how it plays its part. And then we said that when the concentration of the hydronium ion and hydroxide ion are equal, the solution is said to be neutral, which is at a pH of 7. Come on. Start off with today. There we go. Sorry, computer troubles here. Okay, and this is just basically showing you what I just showed you, right? So we just calculated the hydronium ion, pH 0.5 minus 7. Then the hydroxide ion is going to be, if they're equal initially, right? Then if the hydronium ion is greater than 1.0 times 10 to the minus 7, then the hydroxide ion is going to be less than 1.0 times 10 to the minus 7 because you have this nice sliding scale. So that means that the solution is going to be acidic, essentially what I said. Then if the hydroxide ion is greater than 1.0 times 10 to the minus 7, then the hydronium ion is less than 1.0 times 10 to the minus 7. And that solution is called the base. And so this is how we kind of associate it to the pH, right? Because we know that that scale is made. And so the acidity and the basicity of a solution can be expressed as the concentration of the hydronium ion or the concentration of the hydroxide ion. Okay, so when we calculate the pH, we are basically taking the logarithmic values of that. And so that's how we get pH on my, sorry. So we get pH equal minus log concentration of hydronium ion okay. So, and then POH is going to equal minus log of what? Of the concentration of the OH, right? Okay, so altogether, pH plus POH is going to add up to pKw or 14. Does that make sense? You want to see why? Okay, so if we take the log of Kw, and that's going to be equal to, well, let's start one step. Kw equals concentration of H3O plus times concentration of OH minus. So if we take the log of both sides, this is just going to be log H3O plus out of room times OH minus, which is the same thing as saying log Kw So if by definition, minus the log of Kw is equal to pKw, then we minus this entire thing. So we get pKw equals pH plus POH. Since we know that these are the definitions of those, That holds true, right? And then we know that KW was 10 to the minus 14, right? So if we take the minus log of that, that's just going to equal 14. So we have 14 is going to equal, in this case, if it's water, it's going to be 7 to 7, or pH. Since this is a constant, this is always going to be the case. Okay. Okay. Yep. So pKw, that is, right? Yeah. I know it took us a long time to get there, right? But once you see it, you're like, oh yeah, that's pretty cool, right? Yeah. Okay. Can I move forward? Okay, cool. And that's, we already talked about the last slide. So yeah, all these slides were all combined into one. Just okay. So as we know, neutral pH, neutral pOH is going to be 7, right? So we know that if, again, let's take a step back. All this is going to be taking the log of what we've done prior. So we know that it's just going to be pH 7 and pOH 7. And that's going to be neutral. So if the pH is greater than 7, what does that mean? What's that? It's a base, that's right. And then that also means that the pOH is going to be, what's that? It's going to be less than 7, right? Because it's going to act opposite, that's right. pOH is going to be less than 7. Okay, which also means that it's a base, right? Okay, so if our pH is less than 7, then it's a acid. And then our pOH is going to be if it's less than 7, is it, what was our pH? The pH of OH is going to be, it's also going to be an acid, but it's going to be, pH is going to be greater than 7 or less than 7. That's right. So, oops. All right. Or pH is greater. Pac-Man eats the big one. Oops. Greater than 7. Okay. Makes sense? Okay. But yeah, this is also an acid in both cases, right? Because if our pH is less than 7, right? So that means by default, if it's on a scale of 14, let's say our pH is, if our pH is 3. What must our OH be? If our pH is 3, our OH is what? You said 3? Sure. What did we just say about? So pH plus POH has to equal 14. So in this case, POH is 11. Okay, makes sense? Solomon, make sense? It is, right? Yeah, they're flipping scales. Yeah, that's right, exactly. Yeah, so they're both on the scale of 14, but one is like, so if we're talking about the acid goes from 0 to 14, but the base also goes from 0 to 14, but they have different meanings, right? Does that make sense? Yeah. Okay, so if we have a pH of 11, is that an acid or is that a base? It's a base. So then what would be the POH? It would be 3. Okay, make sense? It's so easy to do, yeah. Okay, so if we have a pH of 11, does that mean we have a higher concentration of H plus, or does that mean we have a lower concentration of H plus? If the pH is 11. There we go, good job. Because it's 10 to the minus 11 compared to, that's right. That's right. And that's what I'm trying to get you guys not to do, right? See, assumptions makes ass out of you and me. Did it make sense now? Yeah. Yes, yes. Don't worry about it. It's just going to get a little more confusing when we start talking about redox equations. Okay, so this is just summarizing what we just talked about, right? This table. So this are examples of some acids and then or some substances and how they pertain to being acidic or basic. So for instance, here's water, right? So we know that water has a pH of 7, okay? So all of these guys below it, right, are gonna be more acidic, right? All these guys above it are gonna be more basic, right? So, but the thing is that these guys don't undergo, acid ionization, right? So they don't, is it possible to get a chart like this? Do you guys want a big chart? Is that what you wanting? I'll get you a big chart. Okay, so I'll get you guys a big chart. So, and then if you look down here, these guys undergo complete acid ionization. Basically means that the acid totally dissociates, right? That's complete. These guys here and above are considered to be weak acids, right? They don't dissociate, right? Or they, well, yeah, well, yes, kind of like, so yeah, remember when we talked about electrolytes and then where we had certain acids that were like hydrofluoric acid, right? That acid is a weak acid, so it's not going to have a lot of dissociation. It's going to have a little bit, but not a lot, right? That's what this basically means. There's none, but these guys aren't going to dissociate at all, so they're going to stay together, right? So yeah, if it doesn't dissociate into its ionic components, yeah, So the more it dissociates, the stronger it is. Right? So if you have complete dissociation, it's a really strong acid. Okay. So, and here, these bases don't go through base ionization in water. And then these guys completely dissociate, right? Okay, so then these guys are going to be strong bases, right? Here's water. These are all the different ones. And you guys can kind of see it's kind of dictated by the hydroxide ion. So if you go above the hydroxide ion, you're considered to be a strong, strong base. Okay. So I'll print out this for you guys. Okay. So these guys are all strong acids. Okay, and we know that because they completely dissociate. We've talked about that in last semester. We were talking about ionization. These guys are strong bases. Okay. So this is just an example. So like currently, acid rain makes trees more susceptible to drought and pest infection because it starts to deplete nutrients. And that's, again, because the water now is slightly more acidic than what it should be, right? And that has a lot to do with the carbonic acid, right? Because of CO2. So that's the experiment that we should do. I'll have you guys do towards the end when I bring dry ice in. I'll have you guys do that experiment. What was that? It will be fun. It's a fun experiment. Okay. It also kind of caused corrosions of like the statues that were made from marble and limestone. Why is that? Limestone is basic. That's right. So we're actually breaking it down because of the, don't pop it. You're supposed to sound like me, Grandpa. Yeah. So the way that we basically measure, so we have here, we have a potentiometer. So that measures our pH. You guys are very familiar with that because that's what you guys do with the lab probe. That has a slow response as responding, but hey, it's better than not having anything at all. And these are two examples of it. This is a portable one, pH meter, and then this is a research grade one. And then, of course, we have indicators. We've used the universal indicator. You guys are very familiar with that. We also will be using cabbage, red cabbage extract. And we have pH paper. Right? Did you guys check your soaps today? Okay, so now we're going to talk about the relative strengths of acetic and basic acids. Let's see, what time is it? Let's actually stop, and then we'll take a break. Then we'll get back to this when we start back up. Your lectures may change because, like I said, I have to see if I can recover the file that was wiped out when it crashed. So that has everything consolidated a little bit better, so it's not 116 pages. And then I also had a couple of questions on there too. So okay, so it says calculate the pH of calculate the pH of a 0.0100 molar of sodium hydroxide solution. How would I do that? Okay, set pH equals negative log concentration of the hydronium ion, right? Okay, but what do I have the concentration of? Yes, we have to calculate our POH, right? So our POH is going to equal it's going to be minus log concentration of OH minus. Well, we know that this is this a strong acid or a weak acid? I mean, sorry, strong base or weak base? Thank you. Thank you. See, you're keeping me on my toes. Strong base, right? So we know it's a strong base. So what's going to happen with the strong base? It's going to dissociate. So we get minus log. And since we know that it's moles, molarity, right? We're talking about the molarity, then that's going to be it's going to be a 1-to-1 ratio. So 1 mole of this to the amount of, okay? So then I could say that's going to equal log of 0.0100 molar. So then this is going to be 2. So if POH is 2, okay, that's right. 2 pH is going to equal 14 minus POH, which in this case is going to equal to 12. 14 minus 2. These gates? Okay. So the next one, it says calculate the Ka for a 0.100 molar ionic solution with an equilibrium concentrations of 7.54 times 10 to the minus 6 molar ammonia and hydronium ion. So first thing that we should do is to do what? Something right before the ice table. Can I erase this? What was that? Determine which one is an acid. That would probably be a good idea, but there's one more thing before that. The chemical equation, right? So what is the chemical equation? So we have NH4 in equilibrium with technically this, right? Okay, so then we get Ka. So Ka is typically defined as, it's just the equilibrium constant for the acid. So generic form is Ha at the bottom. I know it looks like I've been drinking. Not yet. I haven't started yet, but maybe a little bit later. Plus. And then in this case, it would be A minus, right? Or, sorry, I got carried away. It's, keep it simple, right? So this would be the Ka of an acid, right? Generic form, right? So in this context, this is what it's going to be. It's going to be the concentration. Right, because this is just equilibrium, right? For a generic acid. So in this case, it's going to be the ammonium ion the denominator, and on the numerator, it's going to be the hydronium ion times the concentration of ammonia. Okay. So it's going to be 7.50 times 10 to the minus 6, and that's going to be squared. Divided by 0.10. Come on. Yeah. Because they're both the same concentration, right? It's Ka. Yeah. K is, yeah, it's the equilibrium constant. Yeah. So it's the equilibrium constant for the acid. Yep. So Kb would be the equilibrium constant for the base. So, and if the acid completely neutralizes the base, then you could use Ka, Kb to calculate, should be equal to Kw. Cold H.
pressure would be 5.62.
Okay. 5.62 times 10 to the -10. Okay, so I'm going to ask you a question. Are we favoring the products being made, or are we favoring the staying together? Why? Yeah. And that means that this concentration, that also lets us know that, right? Because we have more of this than we have of this, right? Okay, so more than likely, you're going to have more of the hydronium ion in solution than you will have of ammonia and water. Or sorry, more of the ammonium. Did I say ammonium? Ammonium. I meant to say ammonium ion than the hydronium ion and ammonia. Ammonium ion and ammonia. Ammonia. Okay. Can I clear? Okay, so what about this one here? Okay. It does. It definitely does. So yes, it has to show the arrow. So that means we have equilibrium being established. So we have Fe H2O 6 2 plus water. We know that this guy's a weak base, so what's going to happen? Oops. What's going to happen? Well, we know because it's a weak base, but yeah, I mean a weak acid, yeah. So, but it's going to favor it, but you're still going to get equilibrium happening. And that's going to be important here, especially when we're talking about weak stuff. Okay, so what's going to be the products? What happens to an acid? It donates what? It donates an H plus. Okay, so that means we get Fe H2O. Oops. Sorry. 5 OH minus. Or OH. And then this is +1 total. Plus, this guy gets an H plus added to it. Okay, so it says basically initially we have this, right? So if we do our ice table, I was waiting for Solomon to tell me ice table. Then initially, this starts off at 0. Our change is negative x, x. Because we've gotten this down to a t. So this is 0.10 minus x. This guy is x. This guy is x. So our k is going to equal which is going to be 1.6 times 10 to the minus. And that's going to equal, what is our expression? Products of reactants, so help me out. F E H2O OH times H3O I have trouble with straight lines. Hopefully I get pulled out of the car. They don't ask me to draw a straight line. And then we got to plug and chug, right? Plug in our values. So we have, let's see, x squared over 0.10 minus x. Let's assume the 5% rule. get, oops, do you mind if I write up here? So we get 1.6 times 10 to the -6 equals x squared. So then x is going to equal 4.0 times root of 2 minus 2. Oops, sorry. I got the 10. Check my math because I did it in my head. That doesn't add up. That isn't right.
1.3
1.3 times 10 to the power of -2.
3 to the power of 10 to the power of
Okay, that makes more sense. What did you get? Everybody got different answers? 1.3? Okay. You have that look. Yeah, that's what I did up here earlier too. I actually, that's a 6. It should be a 6 because when we bring this number over, we're multiplying it. Oh, wait a minute. -8. Oh, that's my fault. And that's why my, yeah. Okay. That should be -8, not -6. See, that's, yeah. Because when you multiply 0.1 times this value, yeah, you plugged it, you did it the right way. I was just doing it in my head. Since I did it in my head, I got carried away with the, yeah. Yeah, I divided it by this number rather than multiplying it by this number. That's why you're not, that's why we have calculators. We don't have to do it in our head. Okay. So then that would give us the concentration of the reactants, right? So then how would I get the concentration of the, I mean, of the products, not the reactants? How do I get the concentration of the reactant? What was that? What is our at equilibrium? We just plug it into here, right? Yeah, so we just plug it in there. Flip it. Is it to the power of -4? Okay. You divide your value, this value here, by whatever value you get. Yeah, just if you do it, so if you get, so you put in that number, so 1.3 times 10 to the -4 divided by 0.1. Yeah, you were really good. Yeah. Yeah. Usually, it's funny, but usually if you pay attention to the number here, and especially if there's not anything being squared or anything like that, your initial concentration, if you look at your initial concentration and your Ka value, if your Ka value is really low, and yeah, then you're usually okay. Usually. So this is to the 4th, right? Put it right. So I'm not allowed to do math in my head right now. Okay, questions, concerns, cash, Kool-Aid. Can I erase? Are we good? Okay. Let's pull up the next question. Come on. Are you out of here? Oh, let me lock it for you. Yeah, you can't lock it. No, that's okay. Okay, how's it going? Ready for the next one? So far? So you guys are starting to see how equilibrium plays a part in the acid basis and how you're still using the same things. There's going to be some little cheap methods that I'm going to show you on Wednesday. Makes things a little bit faster. Okay, calculate the pH for 1.00 molar acetic acid solution. The Ka for acetic acid is 1.80 times 10 to the minus 5. Solomon, help me out. What is it that we know about acetic acid? What type of acid is it? What family does it fall into? Acetic acid. Is it a strong or weak acid? First off, it's a weak acid. Okay. How do we know that it's a weak acid? It's a carbon acid. Carbon acids are always going to be weak. So, yeah. Yes, it is like vinegar. Okay. So, they want us to calculate the pKa for a 1.00 molar acetic acid. Okay, so what does that mean? pKa for, the Ka is so how would I start with this? What was that? Our equation. That's always a good place to start. Okay, so chemical equation for acetic acid. You're saying H2O. Vinegar. It's vinegar. Same thing. Yeah, that's weird that they listed twice. Okay. So we know that this guy is going to be C2. What is the conjugate base of acetic acid? Acetate, that's right. Okay. And then ice table. That's right, ice table. Okay. Starting concentration of acetic acid. Change. Yeah, and I don't know if you guys have had problems. If you don't put zeros, they won't let you finish your homework. You haven't had to do an ice table yet? Okay. Mhm. Yeah. It's like you have to flip through it, and then there's like 5 state. Yeah. That's right. Yeah. Okay. Okay. So we have Ka equals products of reactants. So then that is going to be C2H3 O2 minus in brackets. All over H C2 H3 O2 in brackets. That's going to equal 1.80 times 10 to the minus 5. So what assumptions are we going to make? 5 per circle. So we're going to get x squared over 1.0 molar. So then x is going to equal the square root of 1.80 times 10 to the minus 5. Somebody do that math for me so I don't have to try to do it in my head. 4.24 times 10 to the minus 3. And we'd all agree that that is less than 5%. So then how would I calculate my pKa? Minus log of this value, which is 4.24 times 10 to the minus 3. So it should be yes. Yes, but they're asking for the pH, right? Which is the same thing as the pOH, which is going to give us our X value. So we need to use the X value for that. Does that make sense? Yeah, because that's the only time that we're going to get the hydronium ion is when it's in equilibrium. Because initially it's all connected to acetic acid. Once you get in equilibrium, then you're going to get a little bit, just a little bit of ions if you think it. Okay. Make sense? Yeah. Good. Number 5. 5, and I'm alive. This is a good one. Now, think about shifted a little bit. This is what this is going to do. Can I erase this part? You guys got this? Okay, clear. Let me check something first before. Okay, yeah, we're going to stop there. And then what we'll do is we'll use part of the lab on Wednesday to finish this up, yeah. And then we'll start the experiment. So let's do this one. Okay, so this one is kind of it's a sneaky one, right? So if we think about the acid, this is our acid, right? And we think about the acid dissociation, it's HCN plus H2O. And that's going to yield minus and plus H3. Okay, so AQ, AQ. Okay, so this is just adding what to what side? Was that? Potassium is what is that? A spectator in this case, right? Because this is our equation. So potassium is just acting as a spectator. It's just bringing it to the party. So then what are we adding? Because we know that, was that CN? That's right, CN minus. So we're priming it with CN minus. That's what we're doing in this case. So if we have well, it doesn't change our equation. Our equation is going to be the same, but we're just priming this guy, right? This guy's going to have 0.0500 molar because it's a 1-to-1 ratio. For every 1 KCN, we have 1 CN. Okay, so that's going to be what we're starting off with. And so then it's going to be able to go back to this, right? So then that will be X. So in this case, will be minus X. So for starting over here, this guy is going to be X. And this guy is going to be change the X. This will be X. Be minus X. All right. Yeah. I have to think about it. Okay, so then we'll get at equilibrium, this guy's going to be 0.0500 minus X minus X is going to equal, oops, sorry, X. Then we're going to set up our equation again. Ka equal x over 0.500 minus x minus x. And that's going to equal 6.2 times 10 to the minus 10 So do you mind if I go up here? So I'll get x squared minus see the 1.5 x and that's going to equal 6.2 times 10 to the minus 10x. Well, I guess I could have just done this and got rid of x, huh? That would have been easier. So let's do that. Yeah. So then we'll get 0.500 minus x. So then we'll get plus. This guy will be a minus. So then we'll get x equals. Is that right? Cancel, cancel. It's minus, so then that's plus x. Okay. Equals 6.2 times 10 to the minus. That does not seem right for some reason. X minus x. Cancel that out. Then we'll get this. Acid, right? Is 13. So yeah, that will be acid. Yeah, very, very weak acid. What did you guys get for your value? Was it like x equals 0.5 and 0.00000? 5.0 times 10 to the negative 2. Oh yeah, this is 0. Hold on. 5.0 times 10. So essentially it's the same number, essentially. What was that?
We did the quadratic formula to solve it.
No, I didn't do the quadratic formula to solve it. I could have done the quadratic formula to solve it here. So did you guys use the quadratic formula, or did you guys do it the quick way? Mhm. What was that? Did I add these two x's?
Yeah.
No, I've not added those two x's. Yeah. And you wouldn't need the quadratic formula to solve it, because then you could just use the x divided by x to get that value, right? But then you get a very, because then this is like 1.5 plus this. So then that would be what? X squared equals 1.5.
Oh, I know.
Oh, that should be 0. Here. What do you mean?
For example, when
Oh, I know the problem. Okay, so I messed up on my signs because we're assuming this guy's at equilibrium. So at equilibrium, they both exist, right? So in theory, yes, let me check to make sure I'm right though. No, because then that would switch it. That's right, that would switch it. Because we're priming it with this. But I think this still needs to be a plus, and this has to be a minus, and this has to be a plus. Which should end up with the same, essentially the same answer. Because we're saying at equilibrium, this is the value that the change at equilibrium, right? So we're adding that to what we primed in, right? Where in this case, we're saying that this is going to be subtracted at equilibrium. Well, initially, we're starting out with 0 at equilibrium. So we have whatever, it doesn't make sense. That change. Let me think about it. Let me get back to you on this one, because there's something I'm doing wrong. I can't remember what it is. So I'll get back to you on it. Because that value we're getting, it's going to be a very small value, but it's not going to be, it shouldn't be 0. Yeah, it should be, we should get a value. Because then if we assume the 5% rule, assume that 0, then we end up with just, yeah, which is essentially what we end up with anyway, right? Because the number is so tiny, you know. So I need to figure, there's something I did wrong. I'll have to figure it out. Yeah. It's a good stopping point anyway.